welcome back. All right, so let's do a fast review of the electromagnetic waves. This session is going to last about half hour, maybe about 25 minutes. So the comet pointing away from the sun, the tail of a comet pointing away from the sun.
30 years ago, space was considered a vacuum, except for a curious clue.
It's how the discussion starts regarding the nature of light. Is it composed of particles or is it composed of waves? Newton will argue that it's composed of particles because the particles of light colliding with the particles making up the tail of a comet is going to transfer momentum. Through collisions, the tail is going to get pushed away from the sun. As far as Newton is concerned, argument about light being a wave does not work because waves cannot transfer momentum, they can only transfer energy. So if light creates a compression wave, the particles making up the tail of a comet should only vibrate in the direction of the motion of the wave, or if it's a transverse wave, particles will just go up and down. That's it. They're not going to get pushed away. Huygens is the guy who argues that the light is composed of waves. What's the supporting argument in this case? Number one, wave is a disturbance that carries energy with it. Waves can interfere constructively as well as destructively. So you can make light brighter if you have two light sources, or you can cancel out light and make it darker as it so happens. So that's the argument. All right, so the electromagnetic waves is what you guys are going to test it out. These are three-dimensional transverse waves. They got the electric field component as well as the magnetic field component. And these waves travel at the light speed at a constant speed in a vacuum. So its speed is 300 million meters per second, 189,000 miles per second, or 670 million miles per hour. All right, either way, it's fine. Wave speed can be expressed. It's a combination of wavelength as well as frequency. Frequency can change. If the frequency goes up, the wavelength becomes shorter. If the frequency goes down, the wavelength becomes longer. So this is going to break the electromagnetic waves into an electromagnetic wave spectrum, or it's going to create an electromagnetic spectrum. Frequency is going to go up in this direction. So as the frequency goes up, the wavelength is going to become shorter. All right, so this is our electromagnetic wave spectrum. Highest frequency gamma rays, the lowest frequency radio waves, shortest wavelength gamma rays, highest wavelength radio waves. All right, so the emphasis is on the Maxwell's equation on today's review, because there's stuff that we covered and there's stuff that we didn't get a chance to cover that you're still are going to be responsible for. I'll let you know where you will find that material. All right, so for equations, Maxwell's only contribution is this. How he came up with this is something that you will have to kind of figure out yourself by watching some of my videos. All right, so I'm going to take you there shortly. All right, so the first equation is a statement about the fact that the electric field is generated by the charge itself. Positive charge is going to be the emitter, the negative charge is going to be the absorber. All right, so this is the mathematical expression of that phenomena by Gauss's law. The second statement says that there are no magnetic monopoles. There's no magnetic charge. All right, so the magnetism is always going to be bipolar. It's going to have a north pole, it's going to have a south pole. Once again, this is a reinterpretation of the first formula by Gauss. The third expression is what Faraday came up with. This is the purest form of the Faraday's expression. Change of flux is going to cause a circulating electric field. That's it. So this electric field is what drives the current of the loop, inside the loop. And the last one is this portion of it is the Ampere's law, based on what Ørsted discovered. The current generates a circulating magnetic field. The last statement is the only contribution that Maxwell has. The idea, once again, originates from Faraday. All right, so the changing electric flux creates a circulating magnetic field. That's it. So that's the summary of electricity and magnetism up until 1864. So just about everything that we've done so far in this class goes back to this guy, Faraday. And Maxwell is the guy who was able to formulate everything that Faraday practically, and he discovered when he solved the problem that the electromagnetic waves travel at the light speed. So what does that mean? Which means that the light travels at the light speed, which means that the light is an electromagnetic wave. Once you commit to that, all of a sudden you get into trouble. The problem is, what is the medium that the light disturbs so it can travel at the light speed? Right, so the waves will need a medium to disturb. So what is the medium that the light disturbs so that it can travel at the light speed? Because space is a vacuum, which means that there's nothing that makes up space. The space is the definition of the absence of anything, absence of material. So physicists decided that light being a wave had to have a medium that it could disturb. And they came up with this hypothetical medium that they called ether. It was supposed to be perfectly viscous, without viscosity, let's put it that way. It's going to have tremendous amount of tension, meaning that it's going to be highly rigid, and then it's almost non-existent density. Just so that this disturbance that we refer to as light can travel at the light speed. So it's supposed to be a stationary, non-viscous material which has a perfect density just for light and perfect tension or rigidity for light so that it can travel at the light speed. That's it. So Huygens proposes it, Maxwell goes along with it, and that becomes, all right, I gotta go back. So that becomes the explanation that they came up with at the time. All right, there's stuff that I end up skipping that I don't want to skip. All right, so first step discovers that the magnetism is caused by current. And then introduction of the right-hand rule number 2 to figure out the direction of the magnetic field. And in Faraday's mind, the force that pushes the charges up and down inside the wire when you have an alternating current source generator is the field, the electric field. Obviously, the field emanates or radiates away from the wire itself. So that's how you create the electric field component. When there's current, obviously there's a circulating magnetic field. When you reverse the direction of the current, the direction of the magnetic field changes. So when you have an alternating current source, the AC generator, as the current is going up and down, electric field is also going up and down. Not only the direction is changing, but also the value of the electric field is changing. So this variation of the strength as well as the direction of the electric field is going to keep changing the strength and the direction of the magnetic field. All right, so those two statements that I just mentioned are represented in this section of the formula. This is Faraday's law, which means that if you're varying the strength of the magnetic field in a given region, it's going to cause a circulating electric field in that region. And if you're changing the strength of the electric field within that region, it's going to cause a circulating magnetic field within that region. Okay, so these are right out of Faraday's imagination, how what goes on. So if you vary the strength of the magnetic field, it creates the electric field component. If you vary the strength of the electric field component, it's going to create the magnetic field component. So it becomes a self-propagating field, in essence. Light does not require a medium to disturb. In fact, when they tried to discover or detect ether, it was determined that ether didn't exist. It does not exist. There's no single experiment which was conducted within the past 150 or 60 years was able to detect ether. There's no such thing. So the light, being an electromagnetic wave, does not have a medium that it disturbs. It becomes a self-propagating field. So any variation of the strength of the electric field is going to create the magnetic field component. Any variation of the magnetic field component is going to create the electric field component. As a result, it propagates forward in space at the light speed. And that's it. All right, and then this creates the problem of, from a theoretical perspective, when you're expressing speed, in this case, speed of light moves at the light speed in a vacuum, that begs the question of relative to what? All right, because original thought was there was a stationary background, which was ether, and relative to that stationary background, which is ether, the light was supposed to move at the light speed. We don't have any stationary reference frames in the universe. There's nothing stationary. Everything is in motion. All right. So Einstein asked the question. He says, you know, but what if this point, relative to which the light is moving at the light speed, is also moving at the light speed? Then what? So that's the question that we will address later, starting next week. All right. So the stuff that you need to know. Light is an electromagnetic wave. Definition of a wave is the disturbance that carries energy. All right, so light is a disturbance. Electromagnetic wave is a disturbance. So the energy is going to be carried by the wave, and electromagnetic wave it's a three-dimensional wave. It's got two components. It's got the magnetic field component. It's got the electric field component. Half the energy is going to be carried by the magnetic field component. The other half is going to be carried by the electric field component. That's it. So that's one of the things that you need to know. So the amount of energy carried by the electric field component is the same as the amount of energy carried by the magnetic field component. All right, so out of this, the algebra reveals that the magnitude of the electric field component is going to be significantly larger than the magnetic field component. This expression being the speed of light. So the magnitude of the electric field component is going to be speed of light times larger than the magnetic field component. All right, so this is just a statement of fact. So electric field component is going to be much stronger. So these are undulating waves, which means that they oscillate. So this general expression can be expressed in terms of amplitude of the magnetic field or the electric field amplitudes. Amplitude is going to be changing in time. Average amplitude is going to be 0. As a result, we express it in terms of its non-zero average, which is RMS. All right, so for the multiple choice sections of the test, just watch out for that sort of stuff. All right, so wave intensity. Intensity represents the amount of energy intercepted by a region per second. Some kind of a cross-sectional region, cross-sectional area within that region per second is known as intensity. All right, so this is the amount of power intercepted. Power means energy per second. So this is the amount of energy intercepted per second by that region, area of that region within that space. All right, so the derivation itself is not that important, but the conclusion is important. All right, so the intensity of light. All right, so with the classical physics, when we refer to intensity, obviously this means brightness of light in this case. So the brightness of light is going to depend on its energy density traveling at the light speed. Okay, so the larger the amount of energy that it transfers or carries, the brighter it's going to be. So the energy density can be expressed in terms of the amount of energy, total amount of energy carried by the electric field component or by the magnetic field component. All right, so the energy density carried at the light speed is going to give you the intensity in that case. All right, so cell phones. All right, so here's a problem that I want you guys to focus on. You can find the solution in my handout, or you can solve this problem. Okay, so as you're getting ready for the test, this is a possible test question. It's not complicated, just work on it. I think that Halliday and Resnick, I believe that probably has the solution in it. Okay, so there's a statement here regarding a pointing vector. Average magnitude of the pointing vector. So this signifies the intensity of light. All right, so pointing vector it represents the intensity of light. So if you have to just look that up, that's a statement. So Newton's argument that the light was a particle was because the waves, as far as heat was concerned, could not transfer momentum. However, we know that we got solar cells, obviously. Solar cells obviously will experience force or pressure, radiation pressure. All right, meaning that there's a force acting on the solar cells, which means that force is what changes momentum, which means that force is generating a change in momentum, which means that the force is transferring momentum to the solar cells, despite the fact that they're made up of waves, the electromagnetic waves. All right, once again, the derivation is not that important, but the end result is in this case. So if you have the intensity, if you divide it by the speed of light, it's going to give you the radiation pressure. All right, so intensity of light, this is the total intensity of the experience that you're looking at. You have the incoming light, this is the incident light, so it's going to have its intensity. And then you have the reflected lights, so this is the intensity of the reflected light or the electromagnetic wave in this one. All right, and once again, for the multiple choice section of the test, these are relatively easy problems. Just like I said, my recommendation was that you guys go get a book, something which is affordable or free online. Find problems similar to the problems that use these formulas, just to get an idea. All right, they're not that common. All right, so light is a wave. It's an electromagnetic wave. It's a transverse wave. And that's the conclusion from the classical physics perspective. Okay, so the modern physics is going to have a different conclusion, but from a classical physics perspective, Huygens is correct. Every single problem that we had regarding light, the nature of light, is going to explain why from a classical physics perspective. So that's the conclusion so far. All right. From the lecture lab alum. So the one light travels across a given region. What is that oscillates? What is that oscillates? And what's being transported? What's oscillating is the electric and the magnetic field components, right? And what's being transported is energy as well as momentum. All right, so you transfer not only energy, but also transfer momentum. All right, so how do microwaves cook? All right, so once again, the electromagnetic wave, we are focusing on the electric field component. It's going to be much stronger, obviously. It's much more readily detectable. Also, charges interact with the electric field component. What the microwaves do inside the microwave oven, they will form a standing wave pattern. They will oscillate up and down. I think up to a trillion cycles per second, and they will interact with polar molecules. What is a polar molecule? So when the electric field goes up, the positive charge is going to point in the upward direction. When the electric field reverses direction, the positive charge is going to point in the downward direction. As a result, the water molecules, the polar molecules, will start to spin. Now, as they are spinning, you've got these surrounding molecules. These are neutral molecules. They become polarized. They start shaking and vibrating. Okay, so when the vibration frequency is over a trillion cycles per second, it's known as heat. All right, so that's how the heat is generated. So spinning polar molecules like water molecule is going to set the surrounding molecules into random rotational as well as the vibrational motion, which is known as heat. And this happens through electrostatic attraction as well as repulsion of the surrounding molecules. And so that's how the heat is generated. The fundamental source of electromagnetic radiation is the accelerating charges. If you take a charge and move it up and down, if you accelerate it up and down just like that, it's going to radiate electromagnetic waves. That's it. And the region depends on the frequency of that vibration. So all electromagnetic waves, in essence, will be generated by the same method. The thing you have to do is just accelerate the charges. Accelerating charges will produce electromagnetic waves. All right, so we know that the light moves at the speed of light with respect to an observer on a stationary reference frame like ether. All right, so that was the premise of the derivation that Maxwell came up with. And here's what we know. Given that there are no stationary reference frames in the universe, there's no ether. Does this mean that the light always moves at the light speed relative to us, even if we were to travel at the light speed? The answer to that question is yes. All right, so relative to a reference frame, some kind of a reference frame when you do the calculations, on paper, the light moves at the light speed. If that reference frame on paper is also moving, the light still moves at the light speed relative to that point, right? Regardless of the speed of that point. So regardless of the speed of that point, regardless of the motion of that point, light will always move at the light speed relative to that point. That's the meaning of it. All right, so regardless of, so even if you're moving at the light speed, the light will always move at the light speed relative to you. Only relative to you, the light will move at the light speed. All right, so that's the answer to that question. So we got a welder wearing protective glasses and clothing to prevent eye damage and sunburn. Okay, so what does this imply about the nature of the light produced by the welder? All right, so the sunburn and eye damage is caused by ultraviolet radiation, right? So that's, which means that the nature of light that this person is using is ultraviolet radiation. Ultraviolet and above, the frequency region at and above ultraviolet is considered ionizing radiation, so it can cause cancer, obviously. So you have to protect your skin as much as possible. It can cause skin cancer as well as aging. I want you to go to, the computer is a little bit decided to delete something. Just let's wait for a second. All right, so this is just go into content. Chapter 34, Electromagnetic Waves. So this is the so far everything that you guys have seen regarding electromagnetic waves from conceptual physics as well as college physics. Okay, that builds you up for the engineering physics stuff. Okay, so we didn't have time for the engineering physics stuff, which is fine because now you can do this on your own. Okay, so there are 3 clips that I want you to watch, and there's going to be a test question. The math portion of the test, there's going to be a derivation, and the derivation is going to be extra credit. And I'm going to pick and choose one of the derivations that is included in this one. All right, so you guys have the proper background to be able to follow the derivation at this point. Okay, so I'm going to give you a few hints on what to focus on. So you got 3 clips from my lectures from California. All right, each is about 15 minutes long, and it's going to go over how these 3 equations came about. At least you guys know how this came about, and these are the Gaussian laws. All right, so this is, you guys were tested on this one. All right, make sure that you understand how Maxwell was able to come up with this equation. All right, so this is the Ampere's law. You guys covered this, and then you guys were testing on it. This is important. So this is one of the derivations that I want you guys to focus on. Okay. When I say focus on it, I don't mean just write it on your formula sheet because you guys will have a fresh formula sheet. Don't waste your time on it. Make sure that it's fairly obvious that's coming out of your mind when you put it on paper. Just explain, talk to yourself. Don't do it in the last minute. All right. Okay, this is not understanding. It's not something that you can craft. Make sure that you can understand it well enough to explain it on paper. So this derivation is important. Okay, because despite the fact that Faraday came up with the idea. I'm going to give him credit for it because this is elegant. This is beautiful. This portion of the derivation is beautiful. And then there are other derivations involving putting these two equations together to come up with the electromagnetic waves. Okay, so how did he come up with the fact that all electromagnetics travel at the light speed? He was able to do that by combining this equation and that equation, combining this section of this equation and this equation rather elegantly by using these guys. As this guy, he was able to do that. All right, so it's 3 videos you have to watch to go through the derivations, basically. So the derivations are included in this one. All right, so this stuff is from my California lectures, and this is for engineering physics. Now that you have the background, just figure out the math and just watch it and then play with it. All right, guys, that's it. So